all these are special. And the next case is also special, but it's special in a sense that that is very commonly encountered. So this is linear first order ODE, which is fine. I mean, obviously nonlinear will be more general than linear, but the linear equation is also very commonly because in many cases you can try to linearize your problem and get a linear solution at first. So because of that, you can have a linear equation quite commonly, and to solve a more complicated solution, you might actually want to build up your solution partially, and some of the building block will be 1D equation. So 1D ODE that is linear is very common, and this is also a case that you have a general formula. You have actually at least in the form of integral. You have an integral formula for the solution right away, so you can just plug in the integral and see if you can solve the integral and get a closed form. Otherwise, it becomes something that you just do it integrate numerically. Okay, so it's quite useful. Actually, when you do research, you might use that quite often. So the form is now you go back to the other form. You don't write it as this p dx plus q dy. You write dy dx plus p y. P is a function of x only. Y goes to q. So this is a 1D ODE is a linear because all y just appear in a linear dependency on terms except the inhomogeneous term. So you group all the y terms here. So these are all have the same power of y. So that and power of 1 was obviously is a linear equation. And generally you have a nonlinear inhomogeneous term on the right hand side. So that's the general form. And now your textbook derived that formula. Actually, I think your textbook didn't actually write down the explicit formula, which is string. I mean, but if you read it, you probably can follow a few equations. You can get the final form. But it's trying to derive the form and give you some reason, at least one way to derive this formula. But the formula is simple enough. There might be multiple ways to derive that, and you don't have to do that. You have to follow the textbook way of doing the reason why you get this formula. And one way to justify the formula is just plug that back in, which I found is the most important because I emphasize, once you get a solution, you want to plug that back in the equation and see if satisfied. If it's satisfied, then it's a solution. Right? That's as simple as that. But how you get it is a secondary consideration. Right? So you can just by inspection, you can say just check whether this is true, and you can write it actually because the form is simple enough. It's just one first order derivative, and you have the other term multiplied by a factor. That's suggesting that you get exponential factor out. Because that's just if you have a constant, then obviously you solve without the inhomogeneous term. The solution is just e to the minus px, right? So you know that. So it suggests that there will be exponential factor, and then also there should be a factor that get the q out, get the homogeneous term out, get the inhomogeneous term out, right? You can just write down the formula, try to write down the formula. They say y, and that can include the initial condition, right? And so say the initial condition is you say if y of x0 equals y sub 0, you impose that also in the formula, then you can write the relation like that, y as a function of x, right? Minus y sub 0. And in order that that we cover that, you want your equation have a like the integral, and then it will be 0 at x equals x sub 0. You want it depends on integral, so that automatically satisfies this one, right? And now you also want to recover this inhomogeneous term. So the simple way to recover that is if this derivative will give you a q out, right? And because you integrate to x, so the simple way, if you have q that depends on x prime, and this is dx prime, and take the derivative, we just evaluate q as x prime equals to x, so that will recover that, right? And but then this is not all, because you still have this this px term, p times y term, right? And that we already said that you get exponential function out. Obviously, you want exponential function and minus minus p x, right? So p, and that you get an x out, and originally you have you already have the x prime. You x prime as this integration. So you in this integration, you probably will be using a different notation for x. So like x x prime or x double prime. Try this first, right? So you because now if you write like that, you have exponential factor, something like that. You do the derivative dx dy dx, then you do a derivative to all the dependence of x. So one dependence is this x, but the other is this one, right? And this is exponential factor. When you take the derivative, you get the exponential factor and the derivative of the argument of the exponential function. And because of this x in the integral, you get minus p evaluate x, right? And but then you multiply by the rest, it's still y, right? Right. So
on the exponential term is the limit to x prime.
on
the exponential term, the upper limit x prime is
because yeah, so there are two derivative. One derivative is take the derivative of this one, right? So x all the x prime will you change x prime to x, right? So then if x prime is, if you change x prime to x, that will be, you set this as x prime, right? Then you get the upper limit.
so this is the first integration.
No, I think this is right. I mean Unfortunately, the textbook didn't write it out explicitly. Your textbook has alpha, right? It's alpha. Your textbook has this y equals to 1 over alpha, and then integrate x and alpha q dx plus, right? And then let's see, right? And the alpha equation is given by 5.17. So exponential function of x p dx. I'll take x prime, right? That's 517. You can again also this, I mean, to avoid the confusion in notation. This is depends on x prime, this depends on x prime, this depends on x prime, right? And now you plug that back into here. So this is e to the minus, because it's in the denominator, x prime, and or actual x. This is in this factor, it's just x dx prime, dx prime, right? That's this factor. And then another factor is this one. So e to the integrating x prime, and p is little p dx. But you ought to use x prime, so you use x double prime in this double prime, right? And then multiply by q x prime, dx prime, and then press c. I hate the textbook didn't write it down explicitly, but anyway, now you have a exponential factor here and exponential factor here. You can combine the two. I forgot. This is inside, all inside. X, right? The x prime, yeah, this integral, and then plus a constant, right? So whatever here, you can multiply this into this, and also also the constant term. So you do that. You have a exponential function. You can combine these two exponential factor and get the minus. And it depends on what your choice. You can absorb the minus sign and change this sign, or if you write it like what I did, is minus x over here. So that changed x prime here, the x double prime, double prime. So that's the exponential factor here, right? And then the qx prime, x prime. So the first term, so that's the first term, right? And this is y. And the second term is c times the same exponential function minus x. Well, that is the solution given by a textbook. Okay, but now the textbook that, I mean, this doesn't have fix the lower limit, right? But you can impose that by evaluate the solution at x, right? But before that, you can, like what we did before, check the differential equation. How much time do I have? a few minutes. Like a dy dx. For this one, you just evaluate everything in x prime change to x prime change to x, then this integral becomes 1, becomes 0, the exponential function becomes 1, x prime becomes x. So that will recover the q. Right? When you take the dy dx, the first term will recover the q, right? And the second one will be there's another exponential function, and actually these both have the same exponential factor. So when I take the derivative, you keep the same exponential function, exponential factor, and then derivative of the argument exponential function, and which is just an integral with x in the upper limit or minus sign. So it's just evaluate the integram as x, right? So it becomes minus px and multiplied by the rest, which is y. So this will give minus py, so cancel this one, right? So so that will satisfy the differential equation. Can you follow up my argument? I'm not writing it down because I run out of time. Can you see that? So that take the derivative, the first derivative of with respect to this one, and that will recover this, the right-hand side, right? And the second term of the derivative is the exponential function, which you can go back to here because I separate this. The exponential function is take a derivative is keep the exponential function and take a derivative of the argument, which pull over minus p times the same thing, which is minus py. Minus py plus py is 0, right? So that satisfies the equation, right? And now the idea is you combine. You can check your imposed boundary condition to make it y sub 0. So the y sub 0 will be evaluate everything is x sub 0 here, x sub 0, x sub 0 here, and that will we set the will actually set what the c will be, right? Basically, you want to solve for the c in terms of y sub 0, and then put it back to here and combine to get the formula that I was trying to get at first here. But let's see. But let's check it in next one because I'm right on time. But that would be. I mean, you don't have to impose the boundary condition. You can like use the general equation. Once you get a general equation, and then whatever the boundary condition or initial condition in your problem, you just impose that and figure out what the constant c is. And that is another way to do it. But I mean, you can combine it in the formula or just try to keep a constant. Okay, so that is let's continue on Friday. All right, let's move on because last time we didn't totally finish the first order ODE, linear ODE. When we said that there's a formula, I was trying to at first just use my approach, just guess the form of the solution, and then check it with whether it satisfies the ODE, and that's what I was trying to. But then there was a confusion whether my form is correct, so I went back to compare with the textbook, and then that was fine. So let's finish up what I tried to do, and then once more compare with the ODE. Check it one more time. So let's very quickly repeat the same discussion. The ODE is dy dx plus p x y plus equals to the qx. So this little p and little q is different from this big Q and big P that we used like I said before. But no, that's what we try to do, compare with this. And then I also just for convenience, just set the boundary condition y at x0 equals y sub 0. We want to impose that in the formula also. And last time we started with this y minus y sub 0. The guess, this is a guess, but then we'll finalize that later because we want to make sure that it satisfies this. So this integral of dx prime from x0 to x. That will make sure that at x0, that one will be 0. You get back to the initial condition. And that's what I try to do, qx prime. And then there's exponential function because you want to take the derivative of this part, we'll put our minus p to cancel with this one. We have x p. We already use x prime. So in this integration will be x double prime. And then x double prime. But then you want this, when you take the derivative of that, use x prime becomes x. So this x prime, so that the exponential function, exponential 0 becomes 1. So you recover qx on the right-hand side. So that's I think that's what we stop. And then, but then you found something troubling because if you set q equals 0, that becomes an easy equation to solve. We know how to solve it. But then this is obviously not the solution. Y equals y0 is just a constant. So what you need is fix this term. And so, and then, so that will solve this, and you know how to solve this. This is just when you do it separable way. So it's just this one give you a log, so this will be exponential. That is x dx prime, and then now this can be set to x0 because when x equals x sub 0, that one is 0. Exponential of that is 1. You recover that, so it doesn't change that. When x set to x0, the right-hand side is 0. The exponential factor is 1. Y equals y sub 0. So, right. So that is the guess, because we say q equals 0. Obviously, this is the solution, right? And then with the q term, you add this one. Hopefully, when you take a derivative, then you recover the q over here. All right, so that is a formula that you can use already, but then you can actually move that to the other side just for convenience and get the common factor out. The common factor will be this factor, e to the minus x0 x e y, and then with two terms, one is y sub 0, the other is this term, sub 0 x y y x y. You basically pull out that one, but this one is not exactly this one. There's an x, but then the x sub 0 term is not correct. So you can write in order that this one multiplied by that is given you that. So you want to cancel this x sub 0, and then you keep the x prime, right? Keep the x prime and cancel the x sub 0, or you might as well shift this to the upper limit. So x of 0 is here, point is here, x v double point. Right? Because when you multiply this with that, x here, this is a minus sign, this is a positive sign. So this lower limit cancel. This upper limit becomes but you can keep this x upper limit and strip this back to the lower limit. You can recover that. Okay, so and that's so far so good. Right, so you know what I'm doing, right? So it's just combining this two term into this. Right, this is one. There's no point here. This is the common x. Okay. So this is another formula that you can use, and the good thing about this formula is that there are two factors. One is this exponential factor, and the x dependent is in the argument of the exponential function and in the limit of the integral. So it's this one. And then the second factor, x dependence, is only on this upper limit of this integral. There's no more x dependence in here. Okay, so when you try to check the ODE, the derivative dy dx, there will be two terms. One is taking the derivative of the first term, the other is taking the derivative of the second term. Okay, now you check. Dy dx. Okay, take a derivative of the first term. It's exponential function. So you keep the exponential function and take the derivative of the argument. And the argument is integral, and the dependence of x is in the upper limit. So you basically just substitute the integral. When you see x prime becomes x. Okay, so that becomes minus p x. And you keep the exponential function and multiply by the same factor, so we recover y. But that's the derivative of the first factor. Now, derivative of the second factor is, so you keep the first factor. Right. And derivative of this one is just whenever it's the only dependence is in the upper limit of x. So you basically, you don't, this one is 0. So you basically have x prime change to x, right? Q x e to the that's 0. E. Now we get rid of x prime, you can change that back to d. And you see that this two factor cancel. This q. Okay, so that is the original ODE. Right. So once you write it in this form, to let's take a derivative to directly check that it solved the ODE. And the boundary condition of, obviously, we already did that. When you substitute x equal x0, you recover y equal y sub 0. Okay, so that is straightforward. Okay. So like I said, the textbook should have written an easy to use formula. All this equation is not easy to just plug in because it's very commonly used. So you can either use this formula or that formula. It's just the same. Just which one is more, which one is easier to use. That you just plug in and then see if those integral you can solve. The p integral and q integral, whether that can be integrated in closed form, things like that. Okay. Any question about this?